Imagine for a moment the vast, silent expanse of the cosmos. Picture stars, billions of light years away, burning in their lonely splendor. Consider the immense, almost incomprehensible distances that separate every celestial body, every dust mote, every atom in the universe. In this immense tapestry of space and time, we typically understand that any influence, any signal, any piece of information must travel from one point to another. It might travel at the speed of light, the universe's ultimate speed limit, but it must travel. It cannot simply be in two places at once, or instantly affect something far away without a journey in between. This fundamental principle, that local actions have local consequences, forms the bedrock of our everyday experience, and indeed, of classical physics itself. But what if this deeply ingrained understanding of how reality works is incomplete? What if, concealed within the very fabric of existence, there lies a connection so profound, so immediate, that it defies our most cherished notions of distance and time? Could two entities, separated by light years, perhaps even by the very edge of the observable universe, remain inextricably linked, sharing a secret that instantaneously reveals itself to both, no matter how far apart they roam? This is not merely a philosophical musing, nor the stuff of science fiction, but a core concept at the heart of quantum physics, a phenomenon so peculiar, so utterly counterintuitive, that even its discoverers wrestled with its implications. It is known as quantum entanglement, and it proposes an invisible thread, a cosmic whisper that connects particles in a way that seems to transcend all spatial boundaries. Consider this riddle. You have two coins. You flip one here on Earth, and it lands on heads. Instantly, you know that a twin coin, which was separated from the first and sent to a planet orbiting a distant star, also landed on heads. Or perhaps it always lands on tails if yours lands on heads. There's no signal sent, no communication, no prior agreement that you could have possibly known. The moment you observe your coin, the state of the other, impossibly distant coin, is instantaneously determined. It's as if they shared an unspoken, immediate understanding, a cosmic secret whispered across the void. This isn't quite entanglement, but it starts to give us a feeling for the profound strangeness involved. The quantum version is even more baffling because before you observe either coin, neither coin has a definite state at all. They exist in a hazy, probabilistic superposition of both heads and tails simultaneously. Only at the moment of measurement does reality snap into place for both, in perfect correlation, regardless of how far apart they are. This peculiar interconnectedness, this cosmic secret shared across unimaginable distances, is what physicists call quantum entanglement. At its heart, it describes a situation where two or more particles become linked in such a way that they share the same fate, even when physically separated. When you measure a property of one entangled particle, such as its spin or polarization, you instantly know the corresponding property of its entangled partner, no matter how far away it is. It's as if they are two halves of a single indivisible whole, spread across space. This isn't just a correlation, like knowing that if one glove from a pair is left-handed, the other must be right-handed. That's because, in the quantum world, the particles don't have a definite left-handedness or right-handedness until they are actually observed. It's the act of measurement itself that forces them to choose a state, and they always choose correlated states instantaneously. For centuries, our understanding of the universe has been built upon the principle of locality. This idea dictates that an object is only directly influenced by its immediate surroundings. A billiard ball hits another, a planet's gravity tugs on a passing comet, a light wave illuminates a surface. All these interactions happen locally, or at most, signals travel at a finite speed, never exceeding the speed of light, approximately 299,792,458 meters per second in a vacuum. This cosmic speed limit is a cornerstone of Einstein's theory of relativity, and it dictates that nothing, not even information, can travel faster than light. Yet, quantum entanglement seems to laugh in the face of this fundamental constraint. If measuring one particle here on Earth instantaneously determines the state of its entangled partner on a planet orbiting Alpha Centauri, a star system over 4 light-years away, how can we reconcile this with the universe's speed limit? Does information, in some mysterious way, manage to leap across those vast distances without traversing the space in between? This question has puzzled some of the brightest minds in physics for nearly a century. To truly appreciate the depth of this quantum riddle, let's consider the scale at which these phenomena occur. We are not talking about large, everyday objects like planets or even dust particles. Instead, entanglement typically involves the fundamental building blocks of matter and energy. Subatomic particles like electrons, photons, particles of light, or even atoms. These particles are incredibly tiny, far beyond the reach of our naked eye, existing in a realm governed by rules that are profoundly different from the world we experience directly. Imagine trying to observe something smaller than a speck of dust, so small that its very position and momentum cannot both be precisely known at the same time. These are the elusive dancers of the quantum realm, and it is among them that this invisible link, this cosmic whisper, takes hold. The journey into understanding quantum entanglement is a journey into the heart of reality itself. It forces us to confront our most basic assumptions about how the universe operates, about what it means for something to be real, and about the very nature of information and causality. For those who first grappled with these ideas, it presented a profound challenge to their intuitive sense of a rational, predictable cosmos. How could such a seemingly irrational, instantaneous connection be a fundamental aspect of nature? This initial discomfort, this intellectual struggle, is precisely what makes entanglement such a compelling and important topic in modern physics. It's not just a technical detail, it's a window into a deeper, more mysterious layer of existence. Think of it this way. If you have 2 coins, and you know one is heads, the other is tails, you haven't learned anything new about the nature of the coins, only their relative states. But with entangled particles, until you look, the particles don't have a definite state. They are in a blurred, probabilistic existence, a superposition of all possible states simultaneously. It's only the act of observation that forces them to commit to a single reality. And when they do, their choices are always perfectly correlated, no matter how far apart they are. This isn't just surprising, it's genuinely baffling. It suggests that reality itself isn't fully formed until we interact with it, and that the universe possesses a kind of non-local interconnectedness that transcends our everyday experience. The implications of this invisible link are vast and far-reaching. It challenges our understanding of cause and effect, suggesting a connection that seems to bypass the conventional flow of information. It hints at a universe far more interconnected and strange than we could have ever imagined from our classical perspective. This spooky action at a distance, as it was famously dubbed, became one of the most contentious and debated aspects of quantum mechanics, a theory that otherwise provided incredibly accurate predictions about the subatomic world. The very idea that such a phenomenon could exist, that two distant objects could share an instantaneous bond without any physical medium or signal, seemed to violate everything we understood about the physical world. Yet, as we will explore, this strange connection is not merely a theoretical construct. It is a demonstrable feature of our universe, one that has been confirmed by rigorous scientific experiments. What does it mean for reality if particles can share such an intimate, immediate connection across vast distances? Does it imply a deeper, underlying unity to the cosmos, a kind of fundamental entanglement that pervades all things? Or is it simply a peculiar quirk of the quantum realm, confined to the infinitesimally small and without any direct bearing on our macroscopic world? The journey to answer these questions has led physicists down extraordinary paths, from intense theoretical debates to increasingly sophisticated experiments, pushing the boundaries of what is technologically possible. It has illuminated a universe that is both more complex and more wondrous than our classical intuitions would allow, a universe where the invisible threads of quantum entanglement weave a fundamental part of its very fabric. This phenomenon, once considered a mere paradox, has now become a cornerstone of future technologies, promising capabilities that were once thought impossible. Imagine for a moment the vast, silent expanse of the cosmos. In this immense arena, we naturally expect that any influence, any interaction, must travel from one point to another. Even light, the fastest thing we know, takes time to cross the immense distances between stars and galaxies. We live in a universe where cause precedes effect, where a message sent from one side of a room doesn't instantly appear on the other, but rather travels across the space in between. This fundamental principle, known as locality, suggests that an object can only be directly influenced by its immediate surroundings or by information that has had time to travel to it from a distant source, always respecting the cosmic speed limit of light, approximately 299,792 kilometers per second. It's a very intuitive idea, isn't it? If you push a ball, it moves. If a star explodes, its light reaches us years later. Yet, as we explored, quantum entanglement seems to challenge this very notion, presenting a scenario where two particles, once linked, appear to share an instantaneous, non-local connection, regardless of how far apart they become. This idea, so profoundly counterintuitive, troubled one of the greatest minds of the 20th century, Albert Einstein. His discomfort was not born of ignorance, but from a deep philosophical conviction about how the universe should fundamentally operate. Einstein, the architect of relativity, which firmly established the speed of light as the ultimate cosmic speed limit, found the implications of entanglement deeply unsettling. He famously referred to it as spooky action at a distance. Why would such a brilliant physicist, a revolutionary in his own right, resist such a peculiar aspect of a developing theory? Einstein's worldview was rooted in a belief that the universe was fundamentally orderly, deterministic, and, crucially, local. He believed in a reality where physical properties existed independently of observation, a principle known as realism. For instance, a coin has a definite heads or tails side, even when it's spinning in the air or hidden in your pocket. Its state isn't created by the act of looking at it. Quantum mechanics, with its probabilistic nature and the idea that a particle's state might only become definite upon measurement, seem to undermine this foundational realism. An entanglement, with its instantaneous correlation across vast distances, appeared to shatter the principle of locality entirely. For Einstein, a complete physical theory should describe an objective reality that exists whether we look at it or not, and one where interactions propagate through space and time, not instantaneously. It was in 1935 that Einstein, alongside his colleagues Boris Podolsky and Nathan Rosen, articulated their concerns in a seminal paper titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" This paper laid out what became known as the EPR paradox. Their aim was not to disprove quantum mechanics, but to argue that it was an incomplete description of reality. They believed there must be a deeper, more fundamental layer of reality currently hidden from us that would restore locality and realism to physics. Let's carefully consider the thought experiment they proposed. Imagine a source that emits two particles, let's call them particle A and particle B, traveling in opposite directions. These particles are quantumly entangled. Now, instead of thinking about spin as we did before, let's consider another property, like their momentum and position. According to quantum mechanics, if we precisely measure the momentum of particle A, we would instantly know the momentum of particle B, no matter how far apart they are. Similarly, if we measured the position of particle A, we would instantly know the position of particle B. The crucial point here is that quantum mechanics states you cannot simultaneously know both the precise position and precise momentum of a particle, a principle called the Heisenberg uncertainty principle. So here's the paradox. If we choose to measure the momentum of particle A, we instantly know the momentum of particle B. Since particle B is far away, and no information could have traveled to it faster than light, how did it know what its momentum should be? Einstein and his collaborators argued that if particle B's momentum was determined by our measurement of particle A, then there must have been some spooky action at a distance. This violated locality. Alternatively, they proposed that if quantum mechanics is truly complete, then particle B must have already possessed a definite momentum before we measured particle A. But if it already possessed a definite momentum, then quantum mechanics is incomplete because it claims that the momentum wasn't definite until measured. The same logic applies if we choose to measure position instead. If particle B already had a definite position and momentum, then quantum mechanics is incomplete. This line of reasoning led them to conclude that either spooky action at a distance was real, or quantum mechanics was incomplete. For Einstein, the former was unacceptable. Therefore, he strongly advocated for the latter. To better grasp this hidden variables idea, let's use a simple analogy. Imagine you and a friend each receive a sealed box. Inside each box is a single glove, either a left glove or a right glove. You are told that one box contains a left glove and the other a right glove, but you don't know which is which. Your friend takes their box to a distant galaxy. You open your box and find a left glove. Instantly, you know your friend's box contains a right glove. Did any spooky action occur? No. The information, which glove was in which box, was already determined when the boxes were sealed, long before they were separated. The act of opening your box merely revealed pre-existing information. This is what Einstein and his colleagues suggested for quantum particles. There must be some hidden, pre-existing properties, or hidden variables, that quantum mechanics simply doesn't account for, but which ultimately dictate the particle's states upon measurement. Do you see the elegance of this alternative explanation? It allows us to preserve both locality and realism. The particles aren't communicating instantaneously. Their properties were simply predetermined by these hidden variables from the moment they were created. The measurement merely uncovers what was already there, much like opening a pre-sealed envelope. This perspective offered a comforting return to a more classical, deterministic view of the universe, where chance and instantaneous connections were replaced by a deeper, albeit currently unknown, layer of order. For years after the EPR paper, this debate remained largely a philosophical one. Quantum mechanics continued to be incredibly successful in predicting experimental outcomes. Yet the fundamental questions raised by Einstein, Podolsky, and Rosen lingered. Was the universe truly so strange that particles could influence each other across vast distances without any signal? Or was there a deeper, more complete theory waiting to be discovered? One that would reveal the hidden clockwork governing reality, allowing for a return to a more intuitive, local, and realistic understanding. The scientific community was left in a profound state of intellectual tension. On one side stood the seemingly complete and successful quantum theory, with its inherent spookiness. On the other, the powerful intuition of Einstein, urging scientists to seek a more fundamental layer of reality. This was not merely an academic squabble. It touched upon the very nature of existence. If quantum mechanics was indeed complete, it meant that our classical understanding of an objective, local reality was fundamentally flawed. It implied that particles might not possess definite properties until they are measured, and that the act of measurement itself plays a crucial role in shaping reality. This was a radical departure from centuries of scientific thought, which had always sought to uncover the inherent properties of the world, independent of the observer. The EPR paradox, therefore, served as a profound challenge. It compelled physicists to confront the most unsettling implications of quantum theory head-on. It pushed the boundaries of what was considered scientifically acceptable, forcing a re-evaluation of concepts as fundamental as space, time, information, and even reality itself. But how could one move beyond philosophical arguments and thought experiments to definitively test which interpretation was correct? How could science truly determine if the universe was governed by these elusive hidden variables, or by the spooky action that Einstein found so deeply unsettling? This intellectual impasse, this profound question, would require a new kind of insight, a theoretical breakthrough that could transform a philosophical debate into a verifiable scientific experiment. We have wandered through the serene, almost meditative landscape of the quantum world, encountering particles that seem to share a secret across vast, empty stretches of space. We've explored the profound unease this invisible connection stirred in the mind of Albert Einstein, leading him to famously label it spooky action at a distance. He, along with his colleagues Boris Podolsky and Nathan Rosen, proposed that this apparent instant linkage must be an illusion, a sign that our understanding of reality was incomplete. Perhaps, they suggested, there were hidden instructions, predetermined states, embedded within these particles from the moment they were created, dictating their future behavior. This idea, known as local hidden variables, offered a comforting classical explanation, preserving the cherished notions of locality, that influences cannot travel faster than light, and realism, that objects possess definite properties even when unobserved. But how could one truly know? How could the scientific community definitively determine whether reality was governed by these unseen, pre-programmed instructions, or if quantum mechanics, with its inherently probabilistic and non-local nature, truly held sway? For decades after Einstein, Podolsky, and Rosen published their seminal paper in 1935, the debate remained largely philosophical, a captivating intellectual wrestling match confined to the blackboard and the pages of academic journals. It was a question that seemed destined to forever dwell in the realm of thought experiments, beautiful in their complexity, but seemingly beyond the reach of empirical verification. Then, in the mid-1960s, a quiet, thoughtful physicist named John Stuart Bell entered the stage. Bell, working at CERN, the European Organization for Nuclear Research, possessed a rare gift. He was equally at home with the abstract mathematics of quantum theory and the practicalities of experimental physics. He understood the nuances of Einstein's arguments, the elegance of quantum mechanics, and the deep, unresolved tension between them. While many of his contemporaries had largely accepted the peculiar nature of quantum mechanics because it worked so incredibly well in predicting experimental outcomes, Bell felt that the fundamental question of reality deserved a more definitive answer. Could this seemingly unresolvable philosophical puzzle be transformed into a concrete, testable scientific prediction? Imagine a profound, lingering question, one that touches upon the very fabric of existence, finally being given a clear path to an answer. This was Bell's extraordinary contribution. He didn't try to find the hidden variables themselves, nor did he attempt to directly prove or disprove entanglement. Instead, he devised a brilliant, indirect strategy. Bell realized that if Einstein's local hidden variables were indeed real, they would impose a certain statistical limit on how strongly the outcomes of measurements on entangled particles could be correlated. If quantum mechanics was correct, however, these correlations could be stronger than that limit. Let's try to visualize this with an analogy, something more tangible than abstract quantum particles. Imagine you and a friend, separated by a great distance, each receive one of a pair of special, seemingly identical boxes. Inside each box there are 3 switches. Let's call them switch A, switch B, and switch C. When you open your box and select one of these switches, a light inside will either turn red or green. You and your friend can independently choose which switch to measure. Now, consider 2 scenarios for how these boxes might work. In the first scenario, which aligns with the idea of local hidden variables, each box was pre-programmed at the factory. Before they ever left, a tiny instruction manual was placed inside each box, dictating whether switch A would yield red or green, whether switch B would yield red or green, and whether switch C would yield red or green. The instructions in your box would be perfectly correlated with the instructions in your friend's box for each switch. For example, if your switch A was set to red, your friend's switch A would also be set to red. If your switch B was green, your friend's switch B would also be green. When you choose to measure switch A, you simply reveal its preset color. The act of measuring one switch doesn't influence the others, nor does it influence your friend's box, because all the information was already there, locally stored in each box from the beginning. In this hidden variable scenario, if you and your friend both choose to measure switch A, you'll always get the same color. If you both choose switch B, same. If both choose switch C, same. But what happens if you choose switch A and your friend chooses switch B? Sometimes you'll match, sometimes you won't. Bell's genius was to realize that if these boxes were indeed pre-programmed with local hidden variables, there would be a mathematical limit to how often your results could disagree across all possible combinations of switch choices. Specifically, he showed that the total amount of disagreement between your measurements, summed over all possible choices, could not exceed a certain value. This mathematical statement is what became known as Bell's inequality. It's not about perfect correlation, but about the pattern of correlations and anti-correlations over many trials. Now, let's consider the second scenario, the quantum mechanical one. Here, there are no pre-programmed instructions. The color of the light, red or green, isn't determined until the moment you open the box and select a switch. Before that, the light exists in a superposition of both red and green. And here's the spooky part. When you open your box and choose switch A, and the light turns red, your friend's box, no matter how far away, instantly knows this. If they then choose switch A in their box, it will also turn red, perfectly correlated. But crucially, the act of measuring switch A in your box also affects the potential outcomes for switches B and C in both boxes, in a way that predetermined local instructions simply cannot replicate. In this quantum scenario, the correlations between your choices and your friend's choices and the resulting colors can be stronger and more intricate than what any local hidden variable theory would allow. When you and your friend choose certain specific combinations of switches, the quantum mechanical predictions show that the disagreement value, previously limited by Bell's inequality, would actually exceed that limit. The pattern of outcomes would be so tightly linked, so perfectly intertwined, that no amount of pre-programming or local information could account for it. It would be as if the particles truly were connected by an invisible, instantaneous thread, sharing information in a way that classical physics deemed impossible. Bell's theorem, published in 1964, provided a quantitative measure to distinguish between these two fundamentally different views of reality. His inequality provided a clear, testable boundary. If experimental results violated Bell's inequality, it would provide strong evidence against local hidden variables and, by extension, strong support for quantum mechanics and its spooky action. If the inequality was upheld, it would suggest that Einstein's intuition about a deeper, deterministic reality was correct, and quantum mechanics was indeed an incomplete description of the universe. This was a monumental shift. For the first time, a philosophical argument about the nature of reality could be resolved not by more profound thought, but by carefully designed experiments. Bell transformed the EPR paradox from a debate of ideas into a challenge for experimental physicists. He gave them the blueprint, the mathematical tool, to finally confront the universe and ask, are you truly spooky or merely subtle? The implications of Bell's work were profound. It meant that physicists could, in principle, put quantum mechanics to the ultimate test. They could create entangled particles, separate them, make specific measurements on each, and then compare the results to see if the statistical correlations violated the inequality. If they did, it would mean that either locality, no faster than light influence, or realism, properties exist prior to measurement, or both, must be abandoned. This was a radical proposition, challenging centuries of classical scientific thought. The period immediately following Bell's theorem was one of anticipation. The theoretical framework was in place, but the experimental challenges were immense. Creating truly entangled particles, ensuring their separation, and then measuring their properties with sufficient precision while eliminating all possible classical influences was a Herculean task. It required exquisite control over individual quantum systems and innovative experimental setups. What kind of precise instruments, do you imagine, would be needed to probe the very fabric of reality at such a fundamental level? Bell himself, a humble and brilliant man, initially published his groundbreaking work in a rather obscure journal, and it took some time for its full significance to be widely recognized within the physics community. But once it was understood, the race was on. Scientists around the world began to conceptualize and build experiments that could finally settle the nearly 30-year-old debate ignited by Einstein and his colleagues. These experiments would need to be meticulously designed to avoid any loopholes that could allow local hidden variables to mimic quantum correlations. The stage was set for a series of pivotal tests that would push the boundaries of experimental physics and forever change our understanding of the universe. The question of whether reality was spooky or simply more subtle was about to move from the realm of philosophical speculation to the undeniable verdict of observation. We have journeyed through the perplexing landscape of quantum entanglement, from its initial conceptualization to Albert Einstein's famous dismissal of it as spooky action at a distance. We then saw how John Stuart Bell transformed this philosophical conundrum into a testable scientific hypothesis, offering a clear path to determine whether our universe operates on quantum mechanics' non-local correlations or a deeper, deterministic reality governed by local hidden variables. The stage was set for experiment, but the challenge was immense. How does one actually test something as ephemeral and counterintuitive as spooky action between particles that are potentially light years apart? The answer, at least initially, came not from the cosmic scale, but from meticulously crafted laboratories here on Earth, where dedicated scientists painstakingly probed the very fabric of reality. Imagine for a moment the atmosphere in a physics laboratory in the late 1970s or early 1980s. The air might be thick with the hum of machinery, the gentle glow of monitors, and the quiet, focused intensity of researchers on the brink of answering one of the most profound questions in science. These were not experiments that could be performed with simple instruments. They required cutting-edge technology, extreme precision, and an almost obsessive attention to detail. Bell's theorem, while elegant in its mathematical form, presented significant practical hurdles. To truly distinguish between quantum mechanics and local hidden variables, an experiment needed to entangle particles, separate them, and then measure their properties in such a way that no classical information could possibly pass between them during the measurement process. This meant ensuring that the choices of measurement settings were truly independent and could not be subtly influenced by the particles' shared past or by any hidden pre-programmed instructions. The first significant attempts to experimentally test Bell's theorem began in the early 1970s. Researchers like Stuart Friedman and John Clauser at the University of California, Berkeley, conducted pioneering experiments using pairs of entangled photons. These photons were generated by exciting calcium atoms with lasers, causing them to emit two photons almost simultaneously, with their polarizations intertwined. Polarization is a fundamental property of light, describing the orientation of its electric field oscillation. Think of it like a wave on a rope. You can shake the rope up and down, vertical polarization, or side to side, horizontal polarization, or anywhere in between. For entangled photons, if one is measured to have vertical polarization, its distant partner, when measured along the same axis, will instantly be found to have vertical polarization as well, even though neither had a definite polarization before measurement. Friedman and Clauser's experiments, while groundbreaking, faced certain limitations, often referred to as loopholes. One of the most significant was the locality loophole. In their setup, the detectors that measured the photon's polarization were placed at fixed angles. Critics argued that perhaps the particles, upon emission, could have carried predetermined instructions or hidden variables telling them how to behave at these specific preset angles. These instructions would then perfectly mimic quantum predictions without any spooky action. To truly close this loophole, the measurement settings needed to be chosen randomly, and after the entangled particles had already begun their journey towards the detectors, preventing any prior coordination or pre-programming. This is where the work of Alain Aspect, a brilliant French experimental physicist, and his team at the University of Paris-Sud in Orsay truly shone. In the early 1980s, Aspect and his colleagues embarked on a series of increasingly sophisticated experiments designed specifically to close the locality loophole. Their ambition was not merely to confirm Bell's theorem, but to do so with such rigor that any reasonable doubt about spooky action would be erased. Can you imagine the pressure, the meticulous planning, and the sheer intellectual courage required to undertake such a task, knowing you were challenging the very foundations of classical physics and, in a way, directly addressing Einstein's profound skepticism? Aspect's experimental setup was a marvel of optical engineering for its time. Like their predecessors, his team used entangled photons produced from calcium atoms. However, their innovation lay in how they measured these photons. Instead of fixed polarizers, Aspect introduced a revolutionary system of optical switches. Each switch consisted of a rapidly oscillating crystal that could direct a photon towards one of two different polarizers, each set at a different angle. Crucially, these switches could change their settings incredibly fast, so fast that the choice of which polarizer the photon would encounter was made after the photon had left the source and was already in flight towards the detectors, and before it could possibly reach the other detector. Let's break this down further. The calcium atoms were excited by two lasers, tuned precisely to specific wavelengths, causing them to cascade down energy levels and emit pairs of entangled photons. These photons then traveled in opposite directions, each heading towards its own detection station. At each station, approximately 12 meters away from the source, was Aspect's innovative switching device. These devices were not simple mechanical switches. They were sophisticated acousto-optical modulators. They used ultrasonic waves to create a diffraction grating within a crystal, which could then deflect the photons. By rapidly turning these ultrasonic waves on and off, or by changing their frequency, the researchers could switch the measurement setting, the angle of the polarizer, for each photon within a mere 10 nanoseconds, 10 billionths of a second. Consider the implications of this speed. The photons traveled at the speed of light, approximately 300,000 kilometers per second. Over a distance of 12 meters, a photon takes about 40 nanoseconds to travel from the source to a detector. By switching the measurement setting in 10 nanoseconds, Aspect's team ensured that the choice of measurement angle for one photon was made well after that photon had left the source, and crucially, before any information about that choice could possibly travel at the speed of light to the other photon's detector. This was the elegant solution to the locality loophole. No pre-programming, no hidden variables traveling at or below light speed could account for correlations observed under these rapidly changing conditions. The randomness of the switch settings was also critical, often generated by quantum processes or true random number generators, preventing any subtle deterministic influence. The experiment then involved measuring the polarizations of thousands upon thousands of these entangled photon pairs. For each pair, the settings of the two distant switches were recorded, along with the detected polarization of each photon, e.g., vertical or horizontal, relative to the chosen angle. The data collection was painstaking, requiring long hours and careful calibration to minimize errors and environmental noise. After accumulating a massive dataset, the team analyzed the correlations between the polarization measurements of the distant photons. What they found was truly astonishing. The correlations observed by Aspect and his team consistently violated Bell's inequality, and they did so with high statistical significance. The results were not just a slight deviation. They were a clear and unambiguous confirmation that the predictions of quantum mechanics were correct, and that any local hidden variable theory consistent with classical notions of reality was, in fact, incorrect. The particles were behaving as if they were intrinsically linked, sharing information or states instantaneously, regardless of the distance separating them, and without any discernible signal traveling between them. This wasn't just a win for quantum mechanics. It was a profound reorientation of our understanding of reality. It meant that the universe, at its most fundamental level, is indeed spooky. The properties of entangled particles are not merely revealed by measurement. They are, in a sense, defined by it, and this definition is instantaneously shared across vast distances. The experiments didn't just show that Bell's inequality was violated, they quantified how much it was violated, matching the predictions of quantum mechanics with remarkable precision. The scientific community reacted with a mixture of awe and, for some, continued skepticism. While Aspect's experiments were incredibly robust in closing the locality loophole, another challenge remained: the detection loophole. This loophole arises because detectors are never 100% efficient. If only a small fraction of the emitted photons are detected, it's theoretically possible that the detected photons are not a representative sample of all entangled pairs. Perhaps the hidden variables were conspiring to only allow certain photons to be detected, thereby faking the quantum correlations. Closing this loophole would require even more advanced detectors and experimental setups, pushing the boundaries of what was technologically possible. Despite these lingering questions, Aspect's work marked a watershed moment. It transformed entanglement from a theoretical curiosity and a philosophical debate into an undeniable experimental fact. It laid the groundwork for future experiments that would push entanglement to even greater distances and higher levels of precision, using different types of particles and closing more of the remaining loopholes. The challenge of spooky action at a distance, once a thorn in Einstein's side, had now been empirically confirmed, opening up entirely new avenues for scientific exploration and technological innovation. The universe, it seemed, was far stranger and more interconnected than even its most brilliant minds had initially conceived. After Aspect's groundbreaking experiments in the early 1980s, which solidified the reality of entanglement, the scientific community's focus subtly shifted. The question was no longer if entanglement existed, but how far could this invisible connection truly stretch, and what for? The initial demonstrations, though revolutionary, were confined to laboratory settings, typically spanning mere meters. To truly understand and eventually harness this phenomenon, physicists needed to push its boundaries, overcoming the natural tendency for quantum systems to lose their delicate correlations through interaction with their environment, a process known as decoherence. Imagine trying to keep a whisper perfectly clear as it travels across a bustling city. The further it goes, the more likely it is to be drowned out by other sounds. Quantum entanglement faces a similar challenge. As entangled particles, often photons, travel through a medium like air or fiber optic cables, they interact with atoms, molecules, or even stray electromagnetic fields. Each interaction can act like a tiny eavesdropper, collapsing the fragile quantum state and destroying the entanglement. This is why extending entanglement to greater distances became the next monumental hurdle. Among the pioneers who dedicated their careers to tackling this challenge was Anton Zeilinger, an Austrian physicist often affectionately referred to as the Dean of Quantum Entanglement. His work, beginning in the late 20th century and continuing into the 21st, systematically pushed the limits of entanglement, first across university campuses, then across cities, and eventually into space. Zeilinger and his teams developed sophisticated techniques to generate, maintain, and detect entangled particles with unprecedented precision. They demonstrated entanglement over distances of tens of kilometers using fiber optic cables and then through free space, meaning simply through the air, across the city of Vienna. These experiments were not just about increasing distance. They were about developing the engineering prowess required to send and receive these incredibly faint quantum signals, often involving single photons, through noisy environments. One particularly memorable experiment involved sending entangled photons across a significant natural barrier, the Danube River. While seemingly a simple geographical obstacle, it represented a complex atmospheric path, testing the robustness of their free space quantum links. The photons traveling from one side of the river to another still maintained their spooky connection, affirming that even significant environmental factors couldn't sever the link if the engineering was precise enough. These feats were crucial stepping stones, demonstrating that entanglement wasn't just a laboratory curiosity, but a robust phenomenon that could persist over meaningful distances. But how far could this invisible connection truly stretch, beyond the confines of Earth's atmosphere? The ultimate frontier for long-distance entanglement, and indeed for quantum communication, lay beyond our planet. The atmosphere, even on a clear day, acts as a turbulent, absorbing medium for photons. For truly global quantum networks, a different approach was needed: space. The vacuum of space offers a near-perfect medium for photons to travel without significant absorption or scattering, making it an ideal highway for quantum information. This realization led to the ambitious concept of satellite-based quantum communication. In 2016, China launched a pioneering mission named MISSIOS, or Quantum Experiments at Space Scale, QUES, a satellite specifically designed to test the feasibility of quantum communication over intercontinental distances. This mission, involving teams from both China and Europe, including scientists like Anton Zeilinger, marked a monumental leap. The MISSIOS satellite, orbiting at an altitude of approximately 500 kilometers, was equipped with a sophisticated quantum entanglement source. On board, it generated pairs of entangled photons, which were then beamed down to two separate ground stations on Earth, thousands of kilometers apart. Imagine trying to hit two tiny moving targets on Earth from a satellite orbiting hundreds of kilometers above, with each target needing to receive 1/2 of an entangled photon pair. This required pointing accuracy equivalent to hitting a specific grain of sand on a beach from orbit. The MISSIOS team achieved this incredible feat, successfully distributing entangled photons to ground stations separated by distances exceeding 1,200 kilometers. For context, this is roughly the distance from London to Rome. The satellite communicated with stations in China, like Xinglong and Dellinger, and later even with stations in Europe, such as Graz in Austria. These experiments demonstrated that entanglement could be established and maintained over distances far exceeding any previous terrestrial attempts. paving the way for a truly global quantum internet. The entangled photon pairs, despite their vast separation, continued to exhibit the correlations predicted by quantum mechanics, violating Bell's inequality and reaffirming the non-local nature of reality on an unprecedented scale. But could these spooky links do more than just exist? Could they be harnessed for practical revolutionary purposes? The answer lies in the emerging fields of quantum computing and quantum cryptography, where entanglement plays a foundational and transformative role. Let's first consider quantum computing. Our conventional computers, the ones we use every day, process information using bits. A classical bit is like a light switch. It's either on, representing 1, or off, representing 0, at any given moment. To perform complex calculations, classical computers must process these bits sequentially or in parallel, but always in a definite state. Quantum computing, however, utilizes quantum bits, or qubits. Unlike classical bits, a qubit isn't just 0 or 1. Thanks to a quantum phenomenon called superposition, it can be both 0 and 1 simultaneously. Imagine a spinning coin that is neither heads nor tails until it lands. A qubit is like that coin midair, embodying all possibilities at once. The real power of quantum computing, however, comes from entanglement. When 2 or more qubits become entangled, their fates become intertwined. The state of one instantly influences the state of the others, even if they are physically separated. This means that if you have a system of entangled qubits, they don't just exist in a superposition of individual states. They exist in a superposition of all possible combined states at once. For example, with just 2 entangled qubits, you don't just have 4 possible combinations, 0, 1, 10, 11. You have a superposition of all 4 simultaneously. As you add more entangled qubits, the number of possible states they can simultaneously explore grows exponentially. 10 entangled qubits can explore 2 side 10 or 1024 states at once. 50 entangled qubits can explore over a quadrillion states. This exponential increase in computational space is what gives quantum computers their potential to solve problems that are utterly intractable for even the most powerful classical supercomputers. Imagine searching for a specific book in a massive library. A classical computer might search one shelf at a time, one book at a time. A quantum computer, by leveraging superposition and entanglement, could, in a simplified analogy, explore all shelves and all books simultaneously, finding the answer much faster. This capability holds immense promise for fields like drug discovery, allowing for the simulation of complex molecular interactions to design new medicines. Materials science, enabling the creation of novel materials with unprecedented properties, and even breaking certain types of classical encryption, a prospect that has spurred significant research into quantum-resistant algorithms. The ability to model these complex systems is not merely an improvement. It represents a paradigm shift in our scientific and technological capabilities. Now, let's turn to quantum cryptography, specifically quantum key distribution, QKD, where entanglement offers a truly revolutionary approach to secure communication. In an increasingly interconnected world, protecting sensitive information from eavesdropping is paramount. Traditional encryption methods rely on complex mathematical problems that are hard, but not impossible, for classical computers to solve. Their security is computational. It's assumed that breaking them would take an impossibly long time. Quantum cryptography, however, offers a level of security that is guaranteed by the fundamental laws of physics. Here's how entanglement makes this possible for QKD. Imagine 2 parties, Alice and Bob. want to share a secret encryption key. They can generate a pair of entangled photons. One photon goes to Alice, the other to Bob. When Alice measures a property of her photon, say its polarization, its orientation, the state of Bob's distant, entangled photon is instantly determined. They repeat this process many times, measuring their respective photons in randomly chosen orientations. By comparing a small portion of their measurement choices and outcomes over a public channel, they can establish a shared secret key. The crucial aspect, the magic that entanglement provides, is the inherent security against eavesdropping. If an intruder, Eve, attempts to intercept and measure one of the entangled photons, her measurement will inevitably disturb the fragile quantum state of that photon. Because the photons are entangled, this disturbance will also affect the state of the other photon, the one held by Alice or Bob. When Alice and Bob later compare a small part of their data, they will immediately detect these discrepancies, revealing Eve's presence. It's as if the very act of trying to listen to a conversation changes the words being spoken, immediately alerting the speakers to the intrusion. This means that with entanglement-based QKD, any attempt to eavesdrop is not just difficult, it is detectable. If an eavesdropper is detected, Alice and Bob can simply discard the compromised key and try again. This offers a level of security unprecedented in classical cryptography, making it fundamentally unhackable based on the laws of quantum mechanics. Imagine a world where your most sensitive data, from financial transactions to national security communications, is protected by the very laws of physics, making it fundamentally unhackable. How would that change our digital landscape? This is not a distant dream. Entanglement-based QKD systems are already being deployed in experimental and even some commercial settings. The Messier satellite, for instance, has successfully demonstrated satellite-to-ground QKD, transmitting quantum keys over distances up to 1,200 kilometers, and even establishing a secure intercontinental video call using quantum encryption. These real-world applications underscore the profound shift entanglement is bringing about, moving from a perplexing scientific paradox to a cornerstone of future technologies. The journey from Einstein's spooky action to the satellite-borne quantum experiments and the promise of quantum computing and cryptography is a testament to humanity's relentless pursuit of understanding. It highlights how abstract theoretical concepts, once debated in philosophical terms, can, with ingenuity and persistent experimentation, transform into tangible technologies that reshape our future. Having journeyed through the perplexing landscape of quantum entanglement, from Einstein's initial apprehension to its experimental confirmation across vast distances, we now arrive at a crucial point, understanding its true implications and dispelling common misconceptions. The idea of spooky action at a distance often conjures images of instantaneous communication across the cosmos, a science fiction dream where messages could outpace light itself. But does entanglement truly allow for faster-than-light information transfer? The answer, perhaps counterintuitively, is no. This is one of the most vital distinctions to grasp when contemplating the quantum realm. Imagine, if you will, two individuals, Alice and Bob, each holding one half of an entangled pair of particles. Let's say these particles are photons, and their entangled property is polarization, the orientation of their electric field. When Alice measures her photon's polarization, she might find it to be horizontal or vertical. Due to entanglement, Bob's photon, no matter how far away, will instantly adopt the complementary polarization. If Alice's is horizontal, Bob's will be vertical, and vice versa. The correlation is indeed instantaneous. However, Alice cannot choose the outcome of her measurement. The act of measurement itself is probabilistic, meaning she has an equal chance of finding her photon to be horizontally or vertically polarized. She cannot force her photon to be horizontal to send a yes signal or vertical to send a no. Each individual measurement outcome is fundamentally random. This randomness is the key. Alice might perform a series of measurements, getting a seemingly random sequence of horizontal and vertical polarizations. Bob, far away, performs his own series of measurements, also getting a random sequence. Only after. Alice and Bob communicate classically, perhaps by phone call, email, or a light signal, all of which are limited by the speed of light, and compare their results. Do they discover the instantaneous correlation? They realize that every time Alice measured horizontal, Bob measured vertical, and vice versa. The spookiness lies in this deep pre-existing correlation that manifests only upon measurement, not in the ability to transmit a predetermined message. So, while the universe exhibits these profound, non-local connections, they cannot be exploited to bypass the cosmic speed limit, a principle that remains robust. It's a subtle but crucial point, highlighting the intricate dance between quantum mechanics and the theory of relativity. If we cannot use entanglement for faster-than-light communication, what then are its practical implications? Its true power lies not in breaking cosmic speed limits, but in enabling entirely new forms of communication, computation, and sensing that leverage the unique properties of quantum mechanics. One of the most ambitious and transformative frontiers is the development of a quantum internet. Imagine a global network, not just of classical computers exchanging bits of information, but of quantum devices, quantum computers, quantum sensors, quantum memory units, all interconnected through channels capable of distributing and maintaining entangled states. What could such a network achieve? At its core, a quantum internet promises fundamentally secure communication. As we explored previously, quantum key distribution, or QKD, leverages entanglement to create encryption keys that are provably unhackable. Any attempt by an eavesdropper to intercept the entangled photons immediately alters their quantum state, making the intrusion detectable. This means that sensitive data, from financial transactions to national security communications, could be protected with a guarantee rooted in the laws of physics themselves, a level of security unimaginable with classical cryptography. But the quantum internet extends far beyond secure messaging. It opens the door to distributed quantum computing. Instead of a single monolithic quantum computer, a quantum internet could link smaller quantum processors, enabling them to share entangled states and collectively tackle problems far too complex for any single machine. This quantum cloud could unlock unprecedented computational power for tasks like drug discovery, materials science, and complex logistical optimization, effectively creating a supercomputer by weaving together the quantum resources of many. Beyond computation, a quantum internet could revolutionize precision sensing and metrology. Imagine an array of quantum sensors, perhaps scattered across a continent or even orbiting the Earth, all entangled with each other. By pooling their quantum resources, they could achieve a collective sensitivity far greater than any individual sensor. This could lead to hyper-accurate measurements of gravitational fields, magnetic fields, or even time itself, potentially enhancing everything from geophysical surveys to next-generation navigation systems. For instance, entangled atomic clocks distributed globally could synchronize with extraordinary precision, offering improvements to GPS and fundamental physics experiments that rely on exact timing. The challenges in building this quantum internet are immense, however. Entangled states are fragile. They suffer from decoherence, where interactions with the environment cause them to lose their delicate quantum properties. Developing quantum repeaters that can extend entanglement over long distances without destroying it, and creating quantum memory devices that can store entangled states for useful durations, are monumental engineering feats currently at the forefront of research. Despite these hurdles, ongoing projects in Europe, the United States, and China are steadily laying the groundwork, testing components and building small-scale quantum networks, inching closer to this transformative vision. Beyond its direct technological applications in computing and communication, entanglement is also a powerful lens through which to explore the most profound questions in fundamental physics. It serves as an experimental arena for testing the very limits of our understanding of reality. Scientists are pushing the boundaries of Bell tests, not just with two particles, but with larger numbers, seeking to understand how entanglement scales and where the quantum world transitions into the classical one we perceive daily. Could there be a point where the spookiness fades, or is it an inherent property of the universe at all scales? These experiments are not just about confirming quantum mechanics. They are about probing for potential new physics beyond our current theories. One of the most tantalizing areas of inquiry involves the relationship between entanglement and gravity. Quantum mechanics, with its probabilistic and non-local nature, and general relativity, describing a smooth, deterministic spacetime, remains stubbornly incompatible. Some theoretical models suggest that entanglement might be a fundamental ingredient in a unified theory of quantum gravity. Could the very fabric of space-time, the geometry that dictates gravity, emerge from a deeper network of entangled relationships? It's a truly mind-bending idea, proposing that the universe's large-scale structure might be woven from these invisible quantum threads. For example, some approaches to the black hole information paradox, a long-standing puzzle about what happens to information swallowed by a black hole, involve entanglement playing a crucial role in how information might escape or be preserved. These are deep speculative questions, yet entanglement provides a concrete phenomenon to anchor these abstract theoretical explorations. The philosophical implications of entanglement are equally profound, forcing humanity to reconsider its most basic assumptions about the nature of reality. For centuries, classical physics painted a picture of a deterministic local universe where objects possess definite properties, whether observed or not. Entanglement shatters this intuition. It suggests that reality, at its most fundamental level, might be inherently non-local, where distant events are intimately connected in ways that defy our everyday experience. It compels us to ask, do particles truly have properties before we measure them? Or does the act of measurement, the interaction with a conscious observer or measuring apparatus, somehow create or reveal these properties? This challenges the concept of realism, proposing that perhaps reality is not a fixed objective backdrop, but something more fluid and emergent. How does this fundamental non-locality shape our universe, and what does it mean for our place within it? The practical significance for humanity, therefore, extends far beyond the immediate technological spin-offs. The pursuit of understanding entanglement has already fostered incredible technological advancements, from new types of lasers to sophisticated detectors, many of which have found applications in fields far removed from quantum physics. It is driving the creation of entirely new industries centered around quantum technologies. promising a future where problems currently deemed intractable could become solvable. Imagine breakthroughs in medicine through quantum simulations of complex molecules, revolutionizing drug design and personalized therapies. Consider the impact on artificial intelligence, with quantum algorithms potentially accelerating machine learning and data analysis. But perhaps the most enduring significance lies in our relentless human curiosity. Entanglement is a testament to the power of scientific inquiry to uncover truths about the universe that are stranger and more beautiful than any fiction. It reminds us that our common sense intuition, honed over millennia of interacting with a macroscopic world, is often inadequate for describing reality at its deepest levels. It pushes the boundaries of our imagination, inviting us to embrace a universe that is far richer, more interconnected, and more mysterious than we ever conceived. As we look to the future, many mysteries surrounding entanglement still await exploration. While we have confirmed its existence, its origin remains an open question. Is entanglement a fundamental, irreducible property of the universe, or does it emerge from an even deeper, yet to be discovered principle? The very act of measurement in quantum mechanics, which causes entangled states to seemingly collapse into definite outcomes, is another profound puzzle. What exactly constitutes a measurement? What role does consciousness, if any, play in this process? Scientists are actively pursuing these questions, designing new experiments and theoretical frameworks to peel back yet another layer of reality. Near-future missions will undoubtedly continue to push the boundaries of entanglement distribution, perhaps establishing direct quantum links between continents via networks of satellites. Ground-based quantum internet testbeds will grow in complexity and scale, moving from laboratory demonstrations to robust infrastructure. The development of more stable and fault-tolerant quantum computing architectures will bring us closer to practical quantum computers, and new experiments will continue to probe the interplay between entanglement and gravity, seeking those elusive clues that might finally unify our two greatest theories of the cosmos. So as we conclude our journey into the invisible links governing reality, remember that quantum entanglement, once dismissed as spooky action at a distance by a scientific giant, has transformed from a philosophical paradox into a cornerstone of modern physics and the bedrock of emerging technologies. It is a profound reminder that the universe, at its most fundamental level, operates on principles that challenge our classical intuitions, connecting particles across vast expanses in ways we are only beginning to comprehend. The threads of entanglement weave an intricate tapestry, revealing a cosmos far more interconnected and enigmatic than we could ever have imagined, inviting us to continue our exploration into its endless wonders.